going to reiterate what happened. Free body diagram, I draw my helicopter going from point A to point B. 0 meters per second to 25 meters per second. I do it in 5 seconds. The second thing I want to do is list all my variables: mass, initial velocity, final velocity, and my time. I also want to list what I'm looking for. In the equation, it says right here, it says I want to know the net force and the acceleration. So I put question marks next to those two things I'm searching for. So the third part's the hardest part. I want to do an equation flow chart. Caroline's totally correct. She says, I am going to use equation number 2. When I do equation number 2, I will solve for A, okay? And from A, I will put it down into this equation, F equals MA, and then I can easily solve for F, okay? Does everyone see what's going on? So now it's the simple part. You just put in the numbers in the calculator, right? So I'm going to put this one, I'm going to do this one over here. I'm running out of space. Okay, so I'm just going to write over here. In fact, what I'm going to do is I'm going to have to erase this so I have room, unfortunately. Let's just do this. I'll put 3 over here. So I'm going to put this one. V, which is what? 25 meters per second equals VO, which is 0 meters per second, plus A, I don't know what it is, times 5. And you could do 5 like that so you know it's not an S, right? So what do we end up with? Obviously, this goes to the other side. Subtract 0 anyway, so we don't care. 25 divided by 5 equals A. It ends up being 5 meters per second squared equals A. Everybody good? And then we're going to take that, stick it in this equation. Okay, so I'm going to take this and get this out of my way. You guys got more paper than I do for doing this. So we're going to say F equals 8,000 times 5. Force equals 40,000 Newtonians. Did you get the answer right? Before even doing any of this, right? Did you get the answer right before we did all this? Everyone got the answer right already. You know why? Because you guys are smart. You didn't? Most people are kind of like, oh, I already got the answer. It seems like a lot of, I already got the answer, blah, 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 blah. So you think about it, it was like, the problem right now is easy. But when it gets hard, you're going to say, oh, okay, now I don't know what to do. I don't know how to start. So I'm trying to show you that we take something easy, learn from the easy, then we do something hard. It's way better to do it that way. What's that now?
So the net force is 40,000 newtons?
Yeah, 8 times 5, 40,000 newtons. So what is the units for force? So it's newtons, okay? And based on this definition, this is seconds, right? 5 seconds. It is actually kilograms, right? I'm sorry, this is meters per second squared. I need more room to write this. Okay. It's kilograms. This is meters per second squared. This is a Newton. Okay. That's a force. So that's a lot of work. And everybody should be like, oh my God, are they all like that? Yeah, but they get real easy. And you'll just fire them right off because it's habitual. You just kind of get used of doing it a certain way. And it's not that bad. It just looks horrible, right? Who defined the term net force? Emily did. Total force acting on an object. And what is the relationship between energy and force? Does anybody know? Who have I not picked on? Oh, I know I should call someone from beyond the grave, like Aiden Wood. Aiden!
Energy and force.
Yeah. What's the relationship?
Wait, what question was that?
It was number, I don't know. I could read this thing. Oh, I got it. Number 5.
Oh, they each apply force to each other.
So what happened?
they each apply force to each other.
Anybody have a better one? Oh, Emily.
Well, I said energy makes forces, and forces can transfer energy to other objects.
Right.
I put when the forces change, so does the energy.
Elisa. It looks like she's like totally nervous. I was going to ask her, but she has to deal with this. June. The true definition from a physics point of view. And everybody's kind of like hitting around it. Energy. Equals force over a distance. It's like the most simple definition in the world. It's force over distance. And how do we know that? The work formula. You guys ever heard this? Work equals force times distance? Did you guys talk about that maybe somewhere in middle school? Maybe, maybe not. And work, and I'm kind of doing this, I got room for this. I'm going to pull this all the way up to here for this thing. Work equals joules of energy. So basically, joules equals force, which is kilograms meters per second squared, times a distance, which would be meters. So joules is equal to kilogram meters squared second squared. I wish they would just say that in the book, and they don't. Scoundrels! I don't know why they didn't just tell you that. Joules of energy, right? Same amount of joules of energy, like you say, joules of energy, right? You could actually have kinetic energy, right, equals 1/2 mv squared. You ever heard that? 1/2 mv squared? You might even say potential energy is equal to mass times gravity times height. When you get down to it, look, it's 1/2 mv squared. Let's have some fun with this. 1/2 mass, which would be kilograms, velocity equals meters per second squared. So if we did this thing, this is called dimensional analysis. And we don't care about the 1/2, it doesn't really matter. It equals kilograms meters squared second squared is equal to the same as this over here. It's called, it's the world of dimensional analysis. In fact, I'll put this, I know it was really kind of hard for someone to say, everyone's squinting from the back of the room. Let's go to here and I'll show you what I'm talking about. So here's the work equals force times distance. So we know that the units for this, joules equals, and we know this is newtons times a distance, okay? And we know distance will always be measured in meters for this. And newtons, we know, is equal to force, right? Oh, I'm sorry. Newtons equals, wrong one, eraser. What's newtons equal to? Oh, what? I don't want to buy it. I just want to use it. Okay. Newtons equals mass times acceleration. Okay, look where we're going here. Mass times acceleration in this case would be what? And I'm actually probably should use this instead. Mass is kilograms. Acceleration equals meters per second squared. And if I put a meters over here, I have kilograms times meters squared second squared. That's the units for work. And if we look at, I know you guys saw kinetic energy equals 1/2 mv squared. Somewhere, probably, maybe, last year, I don't know. Did you guys? Maybe not, who cares? But it was the idea behind it was like, it doesn't matter because I could just say 1/2 mass, which would be kilograms, velocity squared, which equals meters squared over second squared. These things are equivalent, right? Potential energy, and this will be a few chapters ahead, equals mass times gravity times height. All right, let's take a look at this. Potential energy equals my mass, which is kilograms. Gravity is always measured in meters per second squared, and my height will always be in meters. When you put this together, you still end up with the same thing. PE equals kilograms, meters squared, seconds squared. So all these units, these things are all the same. I say it's the same thing. It's a joule, 1 joule. So why didn't they just say energy equals force over distance? I don't know. I think you can say energy is what's used to create a force. I agree with that. Need energy to make a force. Everything everybody said in this room was 100% correct. But they didn't give you like the physics, just, I guess it was too much or something like that. I don't think the book was written for kids of your caliber, maybe. I don't know. My way of being polite, I guess. I don't know. All right, ready? Let's do this. Bada bing. We'll go back to this. And we'll continue with this discussion. Now, describe motion of a freely falling object. Use words like speed, acceleration, and distance in your answer. Who wants to tell me about a freely falling object? Speed, acceleration, and distance. Who has a nice little phrase? Fiora, you accidentally looked in my direction. You shall pay the price for that. Now you have to go ahead and tell me. Define motion of a freely falling object. She's like, okay, I don't trust this.
Free falling into an object is due to accelerating speed. And speed due to the force of gravity is pulling it from a distance.
Yes.
Really?
Everything you said is totally right. Right? So let's help with that definition. Freely falling object. So first of all, it's going to, number one, a free fall object will increase in speed. It will have constant acceleration. And its distance will be exponential. When I say exponential, it gets further apart as it goes. So here it is. This may be this is the first second. This is the second second. Third second, the distance is bigger. Fourth second, so the distance gets bigger and bigger as it goes. The distance between the seconds. She's right. Everything you said was totally right. So constant acceleration, and we know for free fall, and we can put it in this class, is going to be essentially 9.81 meters per second squared.
What is the limit of distance?
Distance is exponential. Exponential. And what I'm saying is like it gets bigger and bigger as we go. Remember we did a little tippers thing with the ball? The balls look like they're separating more as it goes on. That's acceleration. We'll look at more of those because those are pretty helpful for looking at them. Totally correct. Okay? You're uncertain, but that's okay. We all are like that. What's the difference between mass and weight? Oh, great. Yes. Yes. You could go outside and drink it and not do an illegal. Illegal is when we pull up our mask. And oh, she's such a good person. Illegal. That's what my son likes to say, illegal. Oh, I thought she's laughing because she pulled out a pack of smokes and she's going to do this. We can have a drink of water. What's that a pack of? Nobody smokes anymore, right? I hope not. But what's funny is like nothing gets bad press like that. Am I recording this? I don't know if I should like. My nonsense. Anyways, back for what? Let's take a look at this. Cool. What's the difference between mass and weight? Yeah, well, because we're gonna punish you for getting a drink of water. It's like a horrible, horrible aspect of life. What would you say? Dang, she nailed that, right? Okay, so this is really, 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 really important, right? So mass, mass equals kilograms. Weight is gravity's effect on mass. He said that very nicely. Okay. $1 billion question. How much do you weigh in outer space, June? If there was like, say you weigh 140 pounds right here, right now on the Earth. If I took you into the middle of space, and let's say, your blood doesn't just vaporize and turn to gas form and you freeze to death in the middle of that. Let's just say I was able to put you on a scale. How much would you weigh in outer space? 0, no gravity. Does that make sense? So that's kind of like a hard thing for people to realize, right? Just you don't have any weight. Weight is actually the measure of the gravity's effect, right? That's so simple. Okay, nice, well played. This one. You drop a feather in a baseball in place where there's no air or vacuum. How will their motions, quote unquote, compare and why?
They'll be the same because there's no air resistance.
Who said that?
Why?
Why? Okay. I can't even spell YouTube right now. That's fine. All right. Feather, hammer, moon, drop. Here we go. I like this one because there's a bunch of beeps. That's it. Here we go. Ready? Hopefully this is really annoying. Hopefully everybody gets the form. Oh, why'd you stop? Here we go.
I guess one of the reasons we got here today was because of the gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. And the feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
Nice. Oh my God. I'm glad we spent those millions and billions of dollars to go do that experiment. I was like, wait, let's close this. Wait. Nice. What did we learn? We're going back to the moon, people. You heard about that, right? Yeah, they said they were. I don't know. Because we're going to put a moon base alpha on the other side of it so we can go to Mars. Because we're going to destroy this planet. We better find another one. So it's a joke. It's a joke. I'm trying to lock and load to get to the air. Yeah, Wally. We're five feet away from that one. Anyways, look at this guy. Explain how to calculate the slope of a graph. I mean, everybody, I'm not going to go into this. It is just the rise over the run. This is the rise. Obviously, this is the run. Everybody should know how to do that. And obviously, you did a bunch of graphs from your race. We're not going to get it. What does the slope of position versus time graph represent? Oh, I can't wait to ask this one to Caroline. What does it represent? So it looks like this. This is position, which is in meters, and time, which would be seconds. So what is this? This is position. This is distance. This is time. You guys did this in a lab. That online thing.
Wait, what?
You guys did this. Yeah, you did.
You did the question?
The rolling ball.
The rolling ball lab. It is the rolling ball lab. You've already done this. What does this equal? Remember, rise over run. And that looks like pies, but run. So I have meters over seconds. So what must it be, Caroline? Yes, it's velocity. Yeah. Did everyone see that? That's easy. Does it make sense? We've already done it. So that's kind of cool, right? Position versus time graph and the speed versus time graph on an object moving. Oh, come on. I can't read this thing. Go back. Wait, let's erase this. I can see what's going on. And this is interesting. Position versus time at a constant speed of 2 meters per second. Well, that's easy, right? So if it's constantly going at 2 meters per second, it would look like this. This is meters and this is seconds. And if we were to look at the speed, this is second and this is meters per second, what would it look like?
It'd be
Here, just-
straight across.
Yes, straight across. Maybe it would look like this, right? That's nice. How can you use speed versus time graph to find an object's acceleration? Here's the big question. Sophia, in the back of the room.
Well, if the speed like goes up, so it's what then it's accelerating.
If it's meter per second here, and this is here, and if it does this slope, and she's totally correct, it is meters per second squared. This is acceleration. Nicely played. Right? Super simple when you really think about it. If we don't mess it up, which we're going to mess it up because we're human beings and screw it all up and it's going to be a mess, right? But does everybody kind of get this? I noticed I was looking at people's homework. Some people drew the little figures. You have to draw like the number line and put 2, 3, 4, 5. You can just draw this in enough that you can say, okay, that's what's going on. That makes sense. Believe me, I'm a lazy person. Join me in the area of laziness. Don't take out graph paper and go crazy. And you don't have to understand the concept. All right, let's take a look. Yeah, we're almost out of time. We've had such a fun morning together. We need more of these. Okay. We're going to look at this. Homework's going to be these things, but watch this. This is great. I got you.
Let's say a jack holds both balls above his head, and then he drops them at exactly the same time. What do you expect to see?
Well, they're going to hit the ground at the same time. I expect them to both land at the same time.
At the same time.
At the same time.
I think they both will. This one hit the ground first. However, they will actually both hit the ground at the same time.
Why is that?
Science. Yeah, science.
Now, the black one clearly feels a lot heavier. So the standard misconception is to believe that the black ball will accelerate at a greater rate and reach the ground first. This year, many people had an idea that both balls would land at the same time, but they didn't know exactly why. I found there were some different misconceptions. For example, many people seem to think that as an object falls towards the Earth, it falls with a constant speed. From this height, yeah, pretty much. Just constant speed all the way down speed.
Yeah, I think it'll be the same constant speed.
I think it's constant. I seem to remember it being constant. I did recently in physics, and I seem to remember that it's the answer.
Whereas the truth is, the speed of both balls is changing all the time. The balls are speeding up as they go towards the ground. That's what the force of gravity does on them. It makes them accelerate. It gets them to speed up. Another misconception I discovered was that some people believe both balls should have the same gravitational force on them, even though the black ball is clearly much, much heavier. The reason I think they said this was because they knew both balls needed to reach the ground at the same time, so they reasoned that the force on them must be the same.
Tell me about how the gravitational force on this ball compares to the gravitational force on that ball.
The force is the same.
It's going to be very similar in terms of gravitational pull. They're both at the same, and they'll fall at the same rate.
I'm not like Einstein, but same gravitational force around the whole world.
Because the gravitational pull on the Earth is the same on both objects.
Are you saying that the force on them is the same?
The pull is the same.
But you felt the pull and you told me the pull is different.
No, I said the weight is different. I didn't say the pull is different.
It is different. It has more gravitational pull. But when I drop them, then they get equal in gravitational pull somehow.
Don't you think it's going to be like 5 times as much?
Yeah, you think, but it's not.
The way you're asking it, yes. The time you're speaking, no.
The gravitational force of both these balls are the same.
This is confusing.
Force on both of these boards is the same.
Is that what you actually believe?
No, but it is.
Tell me what you believe.
I believe we should be more on this, simply for the fact that this is heavier, and just intuition told me that it should be more. But after learning physics, we learned that it is actually the same.
I actually think the force on this ball is more than the force on this ball.
I'm going to give the punchline to the joke because that's who I am, right? So what is going on? It is, ready for this? Here we go. It is, the reason is simple. The bigger the object, the more the force is acting on it. The accelerations are the same. The bigger the mass, the bigger the force. I think as the guy's kind of playing a semantic argument with people and it's screwing with people. I think it's kind of bad that he does that, but in reality, he keeps saying, well, the force of gravity is the same. Oh, it's actually the acceleration's the same on both objects. The force changes depends on the mass. But most people are going to goof that up, except for you, because that's why you're here. But I think he's doing a